Hey guys, I'm Ian. I'm on the team MICROP and Natalia is behind the camera. Today we're going to show you the work we've had on our dynamic system. Glass is on for this demonstration because the laser is fairly bright, and for that reason we'll not be able to demo it in person. It is eye safe, but it is a little hard to look at, so we're going to not go ahead and demo that in person. So if you look behind me, you can see the lasers currently on and going through the galvanometer scanner. It's reflecting off two mirrors to go on the wall. The goal here is to have the transmitter search for the receiver using an algorithm we're actually in the process of developing. The way we're developing the algorithm is by putting it in a simulated environment and running a variety of tests on it to see if it works in the simulated world. So it's not really interesting to show in a demo. What we can show is the work we've done on our driver here. Now, right now, the galvanometer is pointing at whatever preset location the circuit happened to be at, but we can see if I go ahead and input the x-coordinate 10, 10, it'll move. And I can go ahead and put in coordinate 50, 50. It should move a little bit up to the left. And if I do that again to go, for example, to 255, 255, which is our maximum value, we're using 8 bits, you can see it goes way to the top left. And a more interesting little example we can do is show you a sweep. This will show you all the possible points that we can do. So if it's going right now, here we can see the Raspberry Pi that I was just SSH'd into to control the galvanometer. We see here that it uses GPIO pins to connect to the DAC. The DAC then connects to a series of op amps, which then goes to the galvanometer. Looking at a more in-depth circuit diagram, we can see we have the DAC chip here. We use a write pin to ensure that erroneous states are not written while the GPIOs are transitioning. Then, because the DAC outputs currents, we have to use an op amp to turn into a voltage with a feedback back into the DAC. Then we use a buffer to ensure that there's no backwards flow or anything going wrong there. We did have issue with that before, so we added the buffer. Finally, we get our bipolar signal, which is V plus V minus, using a quick -1 gain. And that's what's going on in these op amps right here is the buffer and the -1 gain in one of the op amps part of the DAC. This then is a plus or minus 15 volt differential that goes into the signal, going into the X and the Y driver here that we see are then connected to the mirrors of the galvanometer. As we can see, the galvanometer is two mirrors, which reflect it this way and then that way. Natalia will then zoom in on the mirrors to show us a little bit better what's going on there. You can see that the laser is reflecting off the mirrors and outputting onto the wall over there. As part of this, we have a variety of power sources that we need. Firstly, in order to generate the unipolar signal that we get from the DAC, we use an approximately +7 volt power supply that we see coming in here for our DAC portion. Then we have to step that up to a 15 volt for use with our galvanometer, since our galvanometer actually uses 15 volts at 60 watts, plus or minus 15 volts at 60 watts, with about 2 amps of current. So that causes quite a bit of mess over there, as we need to get specialty power supplies from Leah for that. Part of the reason we had to build our own custom DAC was the inability to use this ILDA controller. Theoretically, the ILDA controller, which is also DMX512 compatible, we would turn off the DMX mode by plugging in an interlock on the ILDA signal. However, there were two issues we found with this, actually many issues. One of them was that the pin wasn't connecting properly. We had to use a very old computer that had the DB25 connector. The second one is that when we try to connect directly to the digital pins, there was a mapping as there's 9 pins here and 25 here. There's some form of mapping happening in this PCB board that we were unable to identify. Similarly, we later found, much to our chagrin, that the entire board doesn't follow the ILDA standard properly, and therefore is essentially unusable, as the datasheet does not identify what ILDA signal to send for different situations. And so we would have had to have used the DMX signal, which is this one. However, that one wouldn't have met the specifications that we needed, as it is very slow, so we weren't able to use it with our 20K PPS galvanometer. Therefore, we had to use our own little custom DAC here with the Raspberry Pi in order to control that.